So, what is the initial stage of solidification? The initial surface of shell is forming below the meniscus. Controlled shell growth is very important, this is desirable quality, you know. So, the solid shell should have adequate thickness and strength that mold exit, otherwise there will be shell rupture and there will be breakout, I have mentioned. So, I have mentioned that the thickness of the solid shell depends on the solidification time at, you know, local solidification time, and since time is, you know, the length of the shell divided by velocity. So, it is related to velocity also, this casting velocity also. As I was telling you, if you have a high casting speed, y will be less. So, this is important, we cannot go to very high casting speed, we have to operate within a limit of higher limit of casting speed, then to get a relatively thicker shell which can withstand the stress, strain which are getting, you know, on it, which are forming a lot of stress and strain. It can be, you know, solidification stress, it can be some mold, you know, when you are bending, when you are straightening the mold, straightening the you know, strand, we can have lot of strain, as I have mentioned earlier. So, these are the important issues we have to remember. Now, this also had discussed that what is the heat transfer along mold depth. I am talking about the horizontal heat transfer through the mold, you know, is a mold which is getting cooled with water, what is the heat transfer across the mold and how the shell is increasing. So, heat transfer is, you know, at the just at the top of the meniscus it is slightly lower and then it goes on increasing. So, from the meniscus at certain depth, at a depth of say 30 millimeter from the meniscus down the mold, we have the peak of, you know, heat transfer, and it is different for different, you know, grades. So, 0.1% carbon, I will discuss later on why heat transfer is relatively less, because, you know, there is a air gap formation, it is a depressions form. I will discuss it details, but this is just to show that how the heat transfer is dependent on the grade of the steel also. So, the heat transfer is at the peak at a certain depth, say 30 millimeter from the meniscus. 0 means top of the mold, meniscus is somewhere here, you do not have meniscus at the top of the mold, otherwise, you know, what is going to happen is due to fluctuation, I mean, there might be spillage which is not desirable. So, the meniscus is at a depth of say 70 millimeter from the top of the mold. So, from the 30 millimeter below that, below the meniscus, you have the maximum heat transfer, and which comes down, you know. Why it should come down? Because solidification is taking place, solid shell is forming, thicker the solid shell as you are coming down. So, less is the heat transfer, you do not require so much of heat transfer, and moreover there is lot of resistance to heat transfer because of the solid shell. So, heat transfer comes down from in the mold from top to bottom. I have also discussed about the cast structure. I have mentioned that this in steel it is not just pure iron. If you have casted pure iron, maybe we have a, you know, plain front of solidification, but since we have lot of solutes, alloying elements in steel, we have carbon, we have silicon, we have manganese, we have phosphorus, sulfur and other alloying elements depending on the steel grade, which will have lot of segregation potential. That means during solidification, the solutes will come out from the solid shell to the liquid. That means you have more enrichment in the liquid. So, as the solidification is taking place, the liquid which is ahead of the solidification front, it is getting more and more rich with solutes. So, because of this, there is a change from the plain solidification front to a dendritic type because of this constitutional supercooling. This is supercooling is due to what? It is due to segregation, that is why it is called constitutional supercooling. All alloying elements will cause segregation, it is less or more distribution of this alloying elements from solid to liquid, or in solid is always less, solubility is less. So, solids will have less amount of solutes and more amount in the liquid. So, liquid is becoming more and more rich as the solidification is progressing. So, this is called constitutional supercooling. So, the liquid steel adjacent to the solid liquid interface will have more segregation. So, there is a, because of that, the solidus of that liquid is less. So, it is called supercooled. So, because of this, the solidification front becomes dendritic. So, initially dendrites grow in specific primary direction near about the direction of the direction of heat transfer in near to that, not exactly to that, because the actual direction takes place certain crystallographic directions of 100. So, 100 which is nearer to the heat transfer direction, that will have the primary direction of dendritic formation. So, it is called primary direction, but after some time there are secondary and tertiary dendrites as well. So, these are important to know that initially it is a dendritic solidification which takes place in steel because of alloy nature. It is basically an alloy, there are a lot of segregation of the solutes. So, it is a dendritic form of solidification. So, at the time of solidification there are 3 zones. The area which has already become solid, that is called solid shell. Liquid pool is there from which solid shell is forming, and in between there is a mushy zone, that means it is a combination of solid and liquid. Solid shell means at that zone solidification is complete. Liquid pool means solidification has not started. Here it is in between, that means the solid fraction in the mushy zone is between 0 and 1. In percentage wise it is between 0 and 100. So, that is called mushy zone, it is a combination of solid and liquid. Now, this macrostructure I will show certain figures, it will be clear. This macrostructure is columnar at surface and central, and then we have equiax at a central, and how this equiax zone increases I have told you, it depends on superheat and electromagnetic study. Now, if you look at the time of solidification what is happening, look at this figure. This is the liquid pool, this is the solid shell which has already formed because of solidification. In between we have a mushy zone, and this relative thickness of the solid mushy zone during solidification will depend on what are the different temperatures. What is the temperature of the solid surface, what is the temperature of the liquidus, this particular temperature liquidus, what is the actual solidus temperature. So, this 3 temperatures, that means the liquidus temperature TL, this temperature TSA, that means the actual solidus temperature, and T0, the temperature on the solid shell, temperature on the surface of the solid shell. These 3 will determine what are the relative thicknesses. So, if you have more of segregation, what is going to happen? TSA, the actual solidus temperature, is getting suppressed. So, the difference between liquidus and TSA increases. So, this becomes low. So, if this becomes low, the mushy zone becomes more wide and the solid shell becomes more narrow. So, relative thickness of the solid shell and the mushy zone is determined by the relative temperatures, liquidus temperature and the actual solidus temperature. Since this temperature is more or less constant, because it is the surface temperature, it depends on the temperature of the mold, or when it has come out of the mold depends on the cooling, secondary cooling. So, this is, we can assume that this is more or less constant temperature. This liquidus temperature depends on the particular grade, but is not very much affected by segregation. So, you know for a particular grade which is liquidus, but because of segregation this actual solidus temperature is suppressed. So, what is happening is with mode of segregation this temperature goes down, that means the mushy zone increases in thickness and the solid shell becomes narrow during solidification. This has lot of implications on the quality of the solid shell, which we will be discussing later on. But please try to remember that at the time of solidification the relative thickness of the solid shell and the mushy zone will be determined by how segregation is affecting this temperature, actual solidus temperature. Mode is the segregation. For certain elements I will be discussing that segregation extent is more. So, the lower will be the solidus temperature because of the impact of that, and lower is this temperature, solid shell will become thin and the mushy zone will become more wide. Now, let us look at how the solid structure actually looks like. I have told that basically there are two broad areas in the solid structure. One is the look at this, these are the mold surfaces here, 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 here. So, we have columnar grains initially, but look at here, just at the mold surface, because of the chilling effect people tell that there are fine equiax grains just at the surface, and then once the solidification goes ahead, just after some time, a few fraction of a second, the columnar dendrites in columnar fashion increases, the primary dendrite goes on increasing in length. So, basically though we have this, but this is only for a few millimeter and only for a fraction of a second during the solidification time we have a surface chill zone, sometimes you may not find this chill zone even. So, what is important is the two broad areas in the cast structure. First is the columnar structure, that means the dendrites are columnar in nature here, and then in the central portion we also have dendrites, but we have equiax. Why equiax grains form here? Because the superheat comes down and due to some segregation or due to some due to generation of some defects or some elements which try to accumulate at the central region, we have heterogeneous nucleation here. So, more number of nuclei form here in the liquid which is solidifying at the last portion of solidification. That means, at the central location of the cast structure we have equiaxed zone, we have dendritic solidification, but in equiaxed shape. Here it is columnar, long dendrites of column. So, what is important to remember is that this ratio of columnar zone is to equiax zone depends on superheat. That means, the actual temperature of the liquid steel which is getting solidified, or during casting what is the temperature of the liquid steel, how high is it relatively, what is the difference of this temperature with the liquidus temperature. So, that is called superheat. Lower the superheat, mode will be the equiaxed zone. That means, if you have high superheat say 40 degree or 50 degree centigrade, you may have columnar zone extending even at this to the center of the casting. That means, you have columnar zone starting from the beginning of the casting to the end of casting. We have hardly any equiax zone if you have relatively high superheat. But if you can cast in a low superheat zone of say 10 or 20 degree centigrade, your equiax zone will be slightly more, maybe 30%, 40%, 20%, starts from 20 to maybe 40, 50%. But for that you must have very low superheat. But as I have mentioned earlier, low superheat is a problem during casting. Your entrapments possibility are there, premature cooling of the liquid might create problem during casting. So, we have to operate at certain superheat, maybe 20 degrees centigrade, not less than that, maybe 15 degrees centigrade, not less than that. So, that means if we have low superheat of say 10 to 15 or 20, we have some amount of equiax zone which is good, as I will be coming later on to the central segregation. If you have this equiax zone, then what happens? The segregation and the cast abnormality at the center gets distributed. If you have high superheat means columnar zone extending to the center, and this the center becomes highly segregated and high amount of solidification shrinkage at the center portion. That means we do not want high amount of segregation, central segregation, we do not want high amount of central porosities in any cast structure, because that is a defect, we do not want that. So, we must have some central segregation, that is one. Another is, I have mentioned that electromagnetic studding during continuous casting helps in making the grains finer, helps in generating equiaxed solidification at the central portion of the casting also. So, we can have less columnar and slightly more equiax zone if we have low superheat, number one, and if we do electromagnetic studding during continuous casting. Nowadays for billet and bloom, people are using electromagnetic studding. This is a typical bloom sort of thing, slightly rectangular, you can have square, you can have some rectangular bloom as well. So, in such solidification, such casting of such steel, it is better to have electromagnetic studding. This facility is not very expensive. Many casters, billet and bloom casters have this facility, where even at slightly higher superheat, maybe at 20-25 degree, you can have maybe say 30% equiax zone, 30-35 equiax zone. So, lower superheat and electromagnetic studding, these two are useful for getting good solidification structure. This I had mentioned earlier, that how the rate of cooling determines the dendrite size. I have mentioned that you have primary dendrites, we have secondary dendrites perpendicular to them, and then maybe we have tertiary dendrites again perpendicular to them. Now, primary dendrites are relatively coarse, then you have secondary dendrites. So, it is normally secondary dendrites thickness are measured to give an indication of what is the size of the casting, what is the size of cast dendrites. So, we measure secondary dendrite spacing. So, this secondary dendrite spacing gives an indication of the coarseness of the cast product. Finer this spacing, lesser this spacing, finer is the cast structure. So, this depends on what? Basically depends on the cooling rate at the surface. That means cooling rate of the heat transfer, at what rate the solidification is taking place, it depends on that. So, you can see higher the cooling rate, finer will be the dendrite spacing. At the surface the cooling rate is more, I have told you, as you are going inside the heat transfer decreases, so the cooling rate also decreases. So, you have relatively coarser dendrites. So, look at the dimensions, maybe at the shell thickness of say 0.6, that means just at the surface, at a time of say 0.1 second, that means when the casting has just started, secondary dendrite spacing is just 10 micron. Now, when we are going to say 10 millimeter at a depth of 10 millimeter shell thickness, that means at a time of local time of solidification of 10 second, after 10 second we are getting a maybe 10 millimeter of shell thickness. So, what is happening there? What is the dendrite size? It started with 10 millimeter, now it has become coarse, it is maybe 60 millimeter. So, that means as you are going inside the cast product, your dendrite size is becoming more and more coarse, because the casting or the cooling rate is becoming less and less as you are going inside. So, at the surface you have fine structure, at the inside you have relatively coarse structure. Same thing will be visible in this figure. Look at what is happening here. This is distance from the stationary slab or mold interface. That means say this is 0 means this is the mold location. As you are going this way means we are increasing the solidification distance. So, the shell thickness is increasing. So, as I have told you, at the surface, at both the surfaces you have columnar zone, in between in the central portion of the casting you have equiax zone. So, in the dendritic zone, columnar zone, this is also dendritic, but equiax dendritic. In the columnar zone, at the surface it is very fine. You see what is the dendrite spacing, secondary dendrite iron spacing, about 50 say. It is increasing to as high as maybe 150 as you are going inside. So, it is a 10-20 steel 50 millimeter thick slab. So, in a slab of 50 millimeter 5 centimeter, you see, as you are going inside the slab from the surface is having finer dendrites. As you are going inside, the dendrite is becoming more and more coarse, columnar dendrites. Then you have equiax zone, and then the other surface, that means solidification is taking place from both the surfaces. Now, from here and here is the slab. So, you see the surface is relatively finer as you are going inside from both the surfaces. The secondary dendrites are becoming coarser, and finally you have equiax zone. As I was telling, then there are two things we have to remember. First, the solid structure is not uniform. It is having a columnar zone near the surface which is extending towards the center, and we have a equiax zone. Now, relatively I have told you equiax zone can be increased in depth by two factors, by taking recourse to two factors. First, low superheat and use of electromagnetic stirring. If you use high superheat and no electromagnetic stirring, that means there may be a situation where you do not have any equiax zone at all, you have only columnar zone extending from both the surfaces. That is not desirable, because the coarseness of the structure at the center, it is goes on increasing as you are going inside, and the final central location you have very coarse structure, you have too much of segregation, you have too much of porosities. So, that area is really bad in quality. Central quality at the central location is bad because of high segregation and high porosity, high shrinkage, solidification shrinkage. So, you require good structure. Good structure means you require relatively more equiax at the central, you require more finer dendrites. If you have coarser dendrites, during rolling there is a possibility of crack formation, because at the boundaries intercolumnar zones there may be a problem, there is normally segregation, there may be a problem, there may be crack generation. So, what is required is a relatively finer dendrites, relatively wide equiax zone at the center. This is what is desirable in a good cast structure. Thank you very much.